Good morning. I am Aljhon Morana from the Department of Civil and Environmental Engineering at Rowan University, and my research focuses on self-consolidating concrete under cold freezing temperatures. My presentation is focusing on its rheological properties. The project is funded by the Cold Regions Research and Engineering Laboratory under the U.S. Army Engineer Research and Development Center. I'm working with my advisors, Dr. Shah Abu Bakri, Dr. Hilson Lomboy, Daniel Kennedy, Dr. Ben Watts, and Seth Wagner. When temperatures go below 4 degrees Celsius, ACI requires concrete be protected from cold weather, and traditional methods include heated enclosures, heated blankets, and heating materials. However, these methods are energy intensive, leading to higher CO2 and cost. Our approach uses cold weather admixture systems, or as we prefer to call it, additive-based frost protection system, or ABFP system, that uses accelerators to hasten hydration and reduce needed protection period. So what is SCC? SCC is a highly flowable and non-segregating concrete that does not need mechanical consolidation to fill forms and encapsulate reinforcement. It has excellent filling ability, passing ability, and stability. On the video on the right, here are the tests for SCC. On the right is the slump flow test, and on the left is the passing ability test, or the J-ring flow test. So basically, we measured the diameter, and that describes how workable your SCC is. This one has a J-ring on it. To say that your SCC has excellent filling ability, the spread diameter with J-ring flow, with J-ring, should be similar to the diameter without the J-ring. We can achieve this excellent properties by maintaining low dynamic yield stress and sufficient plastic viscosity to prevent segregation. Why use self-consolidating concrete for cold weather? Well, cold weather is working under cold weather, especially in freezing temperatures, is less safe compared to working in normal temperatures, but this should not stop us from building necessary structures in cold regions or areas with permafrost. With SCC in cold weather, it allows us to place concrete faster and accelerate construction. It means less working hours, easier placement and consolidation for heavily reinforced structures such as columns and shear walls. With that, we have reduced equipment need and improved work safety and less noise. Our objectives is to study self-consolidating concrete capable of mixing, casting, and curing during cold weather with minimum precautions required to prevent frost damage. Specifically, we aim to investigate the effect of our ABFP system and the cold temperature to the fresh properties of SCC, and determine suitable mixing procedures for cold weather SCC. To develop our SCC mixtures, we use several admixtures. We have high-range water reducer to improve workability, air entraining admixture to modify air content, viscosity-modifying admixture on some of our mixes as viscosity modifier, our ABFP system comprising of accelerator and corrosion inhibitor, and we also investigated using hydration stabilizer to see its effect on the fresh properties of SCC under freezing temperature. Since SCC uses a lot of cementitious material, we also explored adding supplementary cementitious materials, or SCMs. Whenever SCMs are present, they amount to 25% of the total weight of the binder. We classified our SCC into two according to the type of viscosity modifier used. One uses limestone powder, and the other uses viscosity modifying admixture. For every classification, we have three types that differs in mixing and casting and curing temperature, as well as some admixtures used. The first one is mixed and cured at 20 degrees Celsius. We call this as our control mixture. For every type, we have three subtypes that differs on the cementitious materials used. The first one has 100% Portland cement. The second has 25% fly ash and 75% Portland cement. And the third one has 25% slag and 75% Portland cement. Our next type is mixed and cured at -5 degrees Celsius with our ABFP system. And then the last one is mixed at -5 degrees Celsius with ABFP and with added hydration stabilizer. That is a total of 9 mixtures for SEC with limestone powder. The same goes with SEC with viscosity-modifying admixture. So we have a total of 18 mixtures for the whole project. Here are the admixtures used for each mixtures. Notice that we only have VMA on half of the mixtures. We're using limestone powder as viscosity modifier on mixtures on the left. We have ABFP only on mixtures at -5 degrees Celsius, and we added hydration stabilizer on half of the mixtures at -5 degrees Celsius. We adjusted the dosages of these admixtures to achieve these desired properties. A filling ability based on slump flow test, the spread diameter should be between 22 to 30 inches. Passing ability, which is the difference in spread diameter between the slump flow test and the J-ring flow test, which is the one with the J-ring or the blocking. A difference in spread diameter should be up to 1 inch to say that there is no visible blocking, or up to 2 inches to say that there is noticeable blocking but still acceptable blocking. Segregation resistance, we're using a cylinder penetration test or the rapid cylinder penetration test. I have a picture in the next slide. Acceptable penetration for the cylinder is up to 1 inch. If you have more penetration, then you have less segregation resistance. Air content, our target is between 6% and 9%. Here are the key tests that we've done for the project. A slump flow test. We have the slump flow test and the J-ring flow test. Slump flow test for workability, J-ring flow test, when compared to slump flow test, will give you the passing ability. We have the T50, which is the time it takes for the spread diameter to reach 20 inches or 50 centimeters. This is the rapid cylinder segregation, rapid cylinder penetration test. As you can see, there's a gray cylinder there. Before you pull the cone from the slump flow test, you mount this apparatus here. Let the concrete stabilize for 80 seconds and then twist the knob to drop the cylinder for 30 seconds. The amount of penetration will describe the amount of segregation. So if you have more penetration, then you have less segregation resistance. We use the calorimeter to determine the rheological properties. We have the yield stress, plastic viscosity, and thixotropy. We also measured temperature, and all of these tests are done at 0, 15, 30, 45, and 60 minutes after the mixing process. Other tests include air content, freezing point, and compressive strength. We also measured setting time. A standard method for measuring setting time is the penetration resistance test. However, we find this as somewhat impractical, especially for doing it under cold temperatures. So we also explored using ultrasonic pulse velocity, or UPV, to predict initial and final setting times. We have a poster this afternoon for this for the relationship of these two tests. My current results revolve around SEC for limestone powder, SEC with limestone powder only. So this graph is the slump flow versus time graph. At the top is the SEC with Portland cement only. In the middle is the one with the slag replacement. And then at the bottom is the one with fly ash replacement. The red ones correspond to control mixtures, mixed, cast, and cured at 20 degrees Celsius. The blue and the green ones are mixed, cast, and cured at -5 degrees Celsius. Both of them have ABFP, but the green one has an added hydration stabilizer. So our observations, mixtures at 20 degrees Celsius were most flowable right after mixing, and then they continuously lose workability with time. For mixtures, for the blue ones, which is the mixtures at -5 degrees Celsius with ABFP only, they have lower workability right after mixing, increases workability after 15 minutes, and then retains it until the end of the 60 minutes. When added with hydration stabilizer, or the green ones, they needed 30 minutes to achieve the maximum flowability, and however, adding hydration stabilizer also promotes earlier slump loss. This is a penetration depth versus time, or it's a measure of segregation resistance. So our observation here is that mixtures with hydration stabilizer, or the green ones, has less penetration depth or more segregation resistance compared to the ones without hydration stabilizer. So we can say that with more workable mixtures, they may have less segregation resistance. This one is the T50 versus time. So our acceptable value for T50 is between 2 seconds to 10 seconds. So again, T50 is the time it takes for the spread diameter to reach 20 inches or 50 centimeters. So we noticed that for mixtures with ABFP only, without hydration stabilizer, they have acceptable T50 value, 15 minutes to 60 minutes. But for the ones with hydration stabilizer, they needed 30 minutes after the mixing process to have acceptable T50 value. We also measured the rheological properties. Here is the dynamic yield stress versus time. So for control mixtures, the red ones, they have consistent dynamic yield stress over the first hour right after the mixing process. For ABFP mixtures, they have a significantly higher dynamic yield stress right after mixing, decreases after 15 minutes, and then goes consistent until the 60-minute mark. And then for mixtures with hydration stabilizer, they have higher dynamic yield stress right after mixing, goes down for 30 minutes, and then goes consistent from 30 minutes to 60 minutes, which is quite comparable to how the slump flow behaves. When dynamic yield stress decreases, slump flow increases. Plastic viscosity gradually increases with time for all mixtures. We did some, with the resemblance of the rheological properties to the fresh properties, we did some regression analysis. So we have slump flow versus dynamic yield stress. As slump flow increases, as dynamic yield stress increases, workability or slump flow decreases logarithmically. We also compared dynamic yield stress with penetration depth or segregation resistance. So we can say that as dynamic yield stress increases, the penetration depth logarithmically decreases, or it means that as dynamic yield stress increases, you have more segregation resistance. So for T50, we needed both dynamic yield stress and plastic viscosity to predict it. The coefficients reveal that if you have higher dynamic yield stress and plastic viscosity, then you have a higher T50 value. To conclude, from 15 to 60 minutes after the mixing process, SCC at -5 degrees Celsius with ABFP only maintains filling ability and passing ability and segregation resistance requirements, and the flow behavior of SCC at -5 degrees Celsius is determined by its dynamic yield stress and plastic viscosity. Our future work will include analyzing cold weather SCC mixtures with viscosity-modifying admixture, which is half of my mixtures, and compare ultrasonic pulse velocity and penetration resistance of cold weather under freezing temperature. We have a poster this afternoon about this. Analyze isothermal calorimetry data for cold weather SCC. Assess different cold weather concreting techniques considering their CO2 emissions, and develop fiber-reinforced cold weather SCC. Thank you, and that's all for my presentation.